All right, so I think we can start. Yeah, again, thank you very much everyone for joining. We have a very exciting session ahead of us today, a webinar that I think is going to be very interesting for all participants. So we will first cover an introduction on what the GlobalABC Secretariat does here in UNEP, followed by a presentation on GlobalABC's work on building materials and the report on building materials by my colleague Mona here in UNEP. We will then move on to the presentation of the exciting project of Collège Ampateba in Niger by Toby Pear from Article 25. And finally, there will be a Q&A session moderated by Mona afterwards to give you an opportunity to ask questions to Toby or Mona or the GlobalABC staff. So yeah, I think we're ready to start. If we can have the slides up. Thanks, Ijun. So the GlobalABC is an alliance that was founded at COP21. It's hosted by UNEP, the United Nations Environment Programme, and currently stands with 290 members, including 41 countries. The GlobalABC has been developing into the leading global platform for all building stakeholders committed to a common vision of a zero-emission, efficient, and resilient buildings and construction sector. What the GlobalABC does really revolves around four main axes. So it is a global advocate and a catalyst to action. So we advocate for market transformation and focus on catalyzing action by defining carbon neutrality strategy for the built environment. We also advocate for the sector's importance in all global climate action forum, including international high-level events such as COPs, Building Pavilion, and SEMMI as well. It is a trusted platform to set targets and track reports. So the GlobalABC tracks progress in the sector in its annual global status report for buildings and construction, and we encourage our participants to look at the latest publication, and its global climate tracker, which is a new index to track progress in decarbonization in the sector. We also work hard to support countries in setting priorities and measured based on their situation. So for instance, GlobalABC develops policy guidance and global and regional buildings and construction roadmaps, where we outline aspirational targets, timelines, and key action for essential policies and technologies, and offer a model for national and city level buildings and construction roadmaps to support and raise the ambition of NDCs. Lastly, we work hard to support the private sector transition with priorities and strategies, supporting them to change their business models or have their business model focus more on decarbonization and resilience of buildings. So my colleague Mona, for the rest of the session, will present the work of the GlobalABC Materials Hub, which is co-led by the Life Cycle Initiative, the One Planet Network, and the Grid Building Council of Costa Rica. We will then give the floor to our colleagues at Article 25 to present their project on Collège Ampateba in Niger, to discuss lessons learned, showcase the opportunity for emerging economies to leapfrog using leapfrogging away from carbon-intensive building methods and shifting to alternative low-carbon building materials. So without further delay, over to you, Mona.
Thank you, Hanan, and thanks everybody for being here today. I'm happy to be here talking with you about building materials, and just to make sure we're all starting from the same place. Why are we talking about building materials? As Hanan mentioned, the sector contributes quite a lot to the emissions. You can see here we have about 37% coming from the building sector of emissions to the global carbon emissions, both operational and embodied. Embodied emissions are about 10% right now, and we are moving towards decarbonizing the sector. We are focusing quite a lot on the operational emissions, but we need to also decarbonize the embodied emissions, and that means we need to decarbonize the building materials. And so this would include quite a lot of work, but with that in mind, On the next slide, you can see that the GlobalABC works with the Materials Hub to work particularly on decarbonizing of the building materials. And what we do mostly in buildings is really about knowledge generation, dissemination, and implementation. And the next thing is you'll hear quite a lot about the Avoid, Shift, Improve framework to construction materials. And so we'll be going through that. But I also want to flag that in our conversation, only talking about the climate, we are also talking about a just transition. Sorry, what can we say on the slide before? We are also talking about a just transition for we're talking about a just transition. We're talking about health concerns, economic and social concerns, and solving these considerations, including as well the integration of biodiversity. On the next slide, you will see that the Materials Hub work looks at about 4 different ways of doing things. Next slide, please. And there you'll see that we do quite a lot of ad hoc training, and it's really about setting a unified vision for all. Sorry, I see there's a note in the chat about the clarity of the voice, so let me know. Can you hear me okay?
Okay. Mona, I think the connection is not that great. It's the Wi-Fi, I think.
All right, let's try and fix that 1 second. All right. So I think that fixed, but let me know if that still persists. I think we should be able to vision for all the actors in this sector. And then to advocate and identify synergies between the different actors, to ensure that our work is aligned with the SDGs, as well as to identify and pilot solutions and tools and educating the community around that. Has the sound improved?
Yes, thank you.
Okay. All right. Okay, thank you. So on the next slide, you will see that we are going back to the Avoid, Shift, Improve conversation. Don't know if it's just my slides that are slow, but if we can move on to the next slide, please. Yeah. Okay, so on the next slide, you will see a definition. Sorry, the Avoid, Shift, Improve slide. You'll see the conversation about Avoid, Shift, Improve and what it means. I think there's a bit of a lag. That's why I keep on sticking up about that, but sorry about that. So on the Avoid side, we are talking about designing better and designing with less, and building with less. So this is considering a whole life cycle approach to buildings, ensuring that we are being as resource efficient as possible, encouraging local value chains, looking at durability and recycling, and encouraging circular approaches. There's also shifting to alternative building materials, and that's what the essence of today's presentation is about. It's one of these alternative building materials, and that means, of course, developing these materials, but also ensuring that we have supply chains that are developed enough to be used in the market, standardizing and certifying these products, as well as mainstreaming their use in conventional construction. But at the same time, we also acknowledge that concrete and cement and steel will continue to be used in this sector. And so we also need to find ways to improve them and to decarbonize these conventional materials by looking at energy efficiency, by looking at process innovations and the mix that we have in these materials, and any substitutions using natural fibers or others that might be useful. So on this work, in the next slide, you'll see that the Materials Hub focuses their work in 3 areas that align in a way with the work with the Avoid Shift Improve framework. The first is the work on a circular built environment that we do with the Ministry of Environment in Finland and RMIT University and Habitat for Humanity. The second being focused on a whole life cycle policy approach to buildings, which we do with the Department for Energy Security and Net Zero and the World Business Council for Sustainable Development as co-leads. And then the last one is focused on bio-based materials, where we work with the Center for Natural Material Innovation and the Center for Engineers in Argentina. So on the next slide, just a quick snapshot. If you want to join the Materials Hub, please feel free to scan this QR code and join us. We will be sharing these slides after, so don't worry if you're not able to take us the QR code just now. But on the next slide, there's a quick snapshot of a few things that are ongoing right now. For starters, we have an upcoming webinar that's going to focus particularly on data ecosystems for near zero emissions and resilient built environment. At the same time, we're also working to put together a compendium on bio-based materials, and we've already put out a call. So if you yourself are also working on bio-based, and that also includes geo-based materials, please feel free to share with us. This is the QR code to share your submissions. And then we are also taking submissions on the 10 whole life cycle recommendations. If you click on the QR code, you'll be able to see these recommendations and make a submission of your work if you have been using these recommendations. These recommendations were launched during the Buildings and Climate Global Forum as a result of a consensus-driven activity. With participants, with over 100 participants from 40 different countries. So we really look forward to having examples that we can showcase during COP this year. So on the next slide, we're giving you a snapshot of the building materials report that we launched just about a year ago now, but has been quite useful in leading this work and informing this work. This report looked at a variety of materials, including traditional materials such as steel and concrete and plastics and glass, but also alternative materials. And at the same time, took a whole life cycle approach in engaging the variety of sector actors in the value chain of buildings and construction. And so this is also the link to the report for you to take a look. On the next slide, you'll see some of the key messages from the report. The main one being that the building materials are set to dominate climate change, and that this is indeed where we see why we think this work is useful, because it's going to help us reduce the emissions of these materials. And, in between 1995 and 2015, the share of emissions from producing building materials alone grew from 15% to 23%, and it continues to grow still today. And so if we continue under a business as usual scenario, the share of embodied carbon emissions from buildings and constructions, which is mainly going to come from building materials, is actually projected to double by mid-century. So that's where this work is looking at. So on the next slide, the idea is that we are going to look at the carbon impacts of these materials across the whole building life cycle and working with different actors. So here you see a visualization of sources of embodied and operational carbon, and you can see that the life cycle stages highlighted here, and the key message being that the decisions that we make earlier in the life cycle of these buildings are the decisions that have the highest impact as we move forward. And then finally, on the last slide, the pre-last slide, you'll see that we are talking about this avoid, shift, improve strategy. And that's the goal that we're trying to move to by 2050 and 2060. There is no silver bullet to where we are today. And so making sure that we are avoiding waste and building with less, and we're avoiding the extraction and production of raw materials through galvanizing a circular economy, which means we use better data-driven design and use techniques or strategies such as the designing for disassembly, which could decrease about 10 to 50% of GHG emissions, while at the same time maximizing the reuse and recycling of buildings. And renovation right now, for example, generates 50 to 75% fewer emissions than new construction. At the same time, when we're looking at shifting to regenerative material practices whenever possible, we still have to make sure that we're using ethically produced low carbon bio and bio-based building materials. And that could include everything from sustainably sourced bricks to timber, bamboo, agriculture, and forest mass, and to really help incentivize biodiversity as we are doing that. And this shift towards properly managed bio-based materials can also lead to compounded emission savings of up to 40% in the sector by 2050 in different regions. Finally, we have to improve the conventional building materials and processes through decarbonization efforts in the production and increasing the recycling. And in the next slide, you'll see the same figure of avoid, shift, improve, but this time looking at a variety of different materials. And this is one projection of where we could be moving into 2060. And so last but not least, we're focusing on the shift strategy in the final slide. We are looking at shifting towards different building materials. Today, we are going to be looking at a material that falls under earth masonry. And just to flag overall in earth masonry, this is a high quality and a low carbon material that still requires development and adoption of local standards. And that means the work that there's still quite a lot of work that needs to be done at the building codes level and the standards that we're looking at, so we can promote and scale the high quality earth masonry use in the sector. So with that in mind, I'm happy to hand over to Toby, who'll take over and tell us about the material they've been working on and their experience in the field. And Toby, over to you.
Many thanks, Mona, and thanks also to Hanan. Your introduction and description of the work of Materials Hub and GlobalABC is a really good context setter for what I'm going to be talking about today. So just while I share my screen, get the slides up. Hopefully that's visible to everyone, but someone please flag if not. So I'm going to be talking about a project I've been working on for the last four to 5 years with Article 2025. That project is at Collège Chambateba in Niger, in West Africa. And it's an interesting example of material use. So there's this kind of stone called laterite that we use to build the building from. But also in terms of passive design. So the way that we use kind of first principles in the design to reduce reliance on aircon specifically, but the power usage and the operational carbon that accrues over time in future. So first off, a very quick introduction to Article 25. we're an architecture office. We're also a charity, and we're based in London, and we work in humanitarian development around the world. The name comes from the UN's Declaration of Human Rights, which pertains to every person's right to standard of living adequate for good health and well-being of themselves and family, and that includes shelter as well as kind of clothing, food, medical care. So all of our work kind of focuses on those things in one way, and many in several of those ways. So as I mentioned, we're a humanitarian architecture charity. In practical terms, we design and then project manage the construction of healthcare facilities and educational facilities, and sometimes also housing in places where they're greatly needed. Whether we're working with a kind of a primary school in rural Africa, or whether we're working with the UN and government bodies, we always have a very close relationship with the community that we're building for. We don't kind of parachute in ideas that we fancy that day of the week. You know, all of our projects are kind of really derived from the people who are going to use the buildings. So Article 25 has been working for nearly 20 years now, since 2005. We've completed over 100 projects. These range greatly in scale. So just to give you some examples of things we're working on at the minute, we have a new hospital, national hospital in Montserrat in the Caribbean, outpatient buildings in India, orphanage buildings in Tanzania, kind of high-tech research laboratory in Nepal. So we kind of really, our work kind of crosses from really small scale things to kind of larger, and each presents its own challenge. The one I'm going to be talking about today is interesting for a number of reasons. So as I've already mentioned, we're using this material laterite, and very early with the client, we kind of made a few decisions about this project, and we wanted it to be an exemplar project. So one that in certain ways we hoped could be emulated, not just in Niger, but across the Sahel region. So that's kind of the arid southern parts of the Saharan desert in West Africa. And we wanted it to show ways of reducing the carbon use in buildings and also improving the climatic performance, so that the building itself would be a more comfortable place and use less energy operationally. So, you know, these are grand aims, and I think in some ways we succeeded. In some ways, you know, we've got a lot to learn. I'll come to that at the end. So the Sahel is this band of land that spans the whole width of Africa. Sahel is derived from an Arabic word meaning coast, and it's kind of figuratively the coastline that borders the dry Sahara to the north and the tropics to the south. So it has very kind of particular characteristics. It's very dry, very arid. It's quite hot, but it's also more temperate than the desert above. So it has a kind of growing population. It's still fairly it's certainly not densely populated, but more so than the desert above and less so than the temperate regions below. You can get a sense of the landscape in this aerial picture of Niamey. Niamey is the capital of Niger, where the project is located. It's a relatively young city, so it really grew over the last 100 years. Initially, there were fishing communities along the Niger River. And then the colonial times, the French set up cantonments there. And from that, a city kind of grew up over the last 100 years, and it's now swelled to kind of over 1 million people. There's a big dynamic of rural to urban migration, as there is in much of the world. And it's a city that's quite remarkable in my experience. It kind of has a very rural feel, even though it's a city of over 1 million people. Very kind of you see people kind of rearing their animals and selling their wares at every kind of corner, really. So Niger and the Sahel region has a really rich tradition of building and of architecture. It ranges from the nomadic people, so the Tuareg and others who move around the region and so build these incredible kind of demountable structures that they take with them when their flocks move around, to very ancient, in some cases kind of UNESCO World Heritage sites such as Agadez, built almost entirely from mud. Remarkable kind of cities. The openings are very small, the walls are very thick. They deal with the temperatures, which are often around 40 degrees or more, through thermal mass primarily and through shading. But of course, with quick urbanization comes a rapid change, and it's one we see all around the world. So imported materials such as cement, steel, glass, quickly kind of adopted, but not always well understood. You can kind of, this was a picture I took out of the window of the car, but often kind of used in quite confused manner. These big panels of glazing without protection are completely inappropriate for a Sahelian climate. They're going to create very hot interiors that will need air conditioning when power supply is unreliable. You can see what happens very, very fast. So it poses big questions, that as an architect, as development body, how do we address these challenges of a very, very challenging climate, a nation that is not well industrialized? How do we build for Niger today? What's an appropriate way to build? So these questions that, I don't necessarily have all the answers to, but I'll certainly make the case for laterite as a locally available natural building material. It has many, many benefits in my view, both in terms of kind of the obvious environmental pluses. Its embodied carbon is very low. Transport carbon is very low. It can be dug out by hand. You don't even need machinery. This is a really, really low carbon material. There are no emissions related to its use. There are also benefits economically. When you have a locally available material, it kind of reduces reliance on international networks and importation. This became very clear during this construction when COVID hit. The cost of steel went through the roof. We couldn't even procure any for months on end. The building process stopped, whereas, if you're able to build with local materials, those risks are hugely reduced and costs are kind of much more controlled. You also keep that money locally, if you're using locally procured materials. There are cultural advantages. This building is of Niger. It speaks of the desert it's from. And it also has big advantages over cementitious materials in terms of comfort. It's more breathable. You find there are kind of advantages to the way it cools the buildings internally. So there are lots of reasons to use this material. And I haven't even mentioned the kind of aesthetics that we will come to. That's obviously subjective, but I certainly think it's far more beautiful than a kind of cement block wall, for instance. So a little bit more context. Niger is a poor country. It's been bottom of the UN's development index for many of the recent years. Very few students enroll in further education. This results in a low literacy rate, has a very high birth rate, over 7 children per woman, which certainly a couple of years ago was the highest on the planet. And this is a kind of cycle, the more children there are, the harder it is to educate everyone, and so on and so forth. So providing good education and comfortable classrooms is clearly a really, really vital factor in improving life for Niger's young generations. So we were invited to work with College Hampate Bar. Now, this college already existed. These buildings were built back in the 2000s. These are classroom buildings. College Hampate Bar is providing education for everyone, so it subsidizes school places for those families that can't afford to pay for them. And they came to us asking for help in expanding their facilities, providing up to 1,200 students. And so we spent a lot of time kind of building a team to do that. The way that Article 25 work is for projects like this, where we can, we pull in pro bono engineering in London. So we did that for this project. The structural engineers and the services engineers were providing their input for free. And then we collaborated with Kodjo, who's originally from Ghana, but based in Burkina Faso, and very familiar with Niger after years of working there too, to be our kind of project architect and site manager. And then a contractor again from Burkina Faso. Now, the reason for this was for the use of laterite, which I'll come to shortly. The design was developed with close collaboration with the school and the students and the teachers, really figuring out what they needed, what the priorities were, what didn't work well with their existing classrooms. And clearly the problem of heat and discomfort in the classroom was a focal point. It gets really, really hot. So I've been there in April time when it's been 46, 47 degrees, and it's really hard to think or to work effectively in those kind of conditions. And students and teachers both pulled this up repeatedly. I won't dwell too much on the design, but just to give you a little bit of an idea, this image shows the site before we started work. So there were some fairly good classrooms, those kind of the long run up here that were built maybe 15 years prior that needed some refurbishment work. Then there were some very poor condition single block classrooms here, which they wanted to phase out. And kind of some very, very nasty latrines and an administration block that also needed some refurbishment work. So in the spirit of keeping the buildings you could, we kind of came up with refurbishment proposals for those existing buildings, but then also in terms of expanding, we designed new classroom blocks for the lycées, so the older college students, as well as an upgraded water and electrical supply, and new latrines and a guards post and a few more kind of office spaces for the staff. So this was the kind of scope of the project. It was started on site in 2019, and then with COVID providing all sorts of delays, we wrapped up most of that in early 2022. There are designs in place for much bigger expansion, so for the primary school and for science lab, assembly hall, library, lots of landscaping. That's all currently kind of being considered by the client, and they've got kind of questions about what they want to do and the funding and all sorts, but that has yet to happen. So onto the passive design. So this is not something we dreamt up ourselves. This is kind of derived from a tradition of building double roofs in the region, but also popularized by Francis Kéré, who many of you may know. He's a Burkinabe architect, and he's been building schools in Burkina Faso using variations on this technology for years. The principle is to provide a roof space between a kind of large overhanging shading roof, which here is in metal, and then a lower kind of ceiling. So by angling this roof to the prevailing wind, you can draw airflow through, Now, when the hot sun hits the top metal roof, you prevent it radiating into the classroom spaces by drawing the air through, having a kind of ceiling to soak up, ideally with some mass to soak up some of that radiated heat. And then you also have lots of openings in the classrooms themselves, which encourage cross ventilation. And this also seems to have some impact on pulling the air through the roof space as well, which heightens the effect of the double roof and keeps temperatures as low as possible in the classroom. Our classroom blocks were very simple in plan. So they were blocks of 4 classrooms with a shaded kind of study space in the middle. Keeping the design quite simple, so it wouldn't be too complex for construction, but we had these walls which we wanted to build in laterite on a plinth kept off the ground because there were problems with flash flooding. So you want to keep this laterite well away from water, which it wouldn't do so well in. Then the roof is tied with a concrete roof beam. So we're using concrete and cement where we need it, but minimizing its use to kind of essential moments, as Mona alluded to. And then above the concrete ring beam, we have earth brick vaulting, which is supported on that ring beam and on the bottom of these steel trusses. Oh, apologies. And then a metal sheet roof on the top. So we've got a metal sheet roofing for the top roof and then earth vaulting for the lower roof. You can see them here. This is a kind of visual we produced before the building was constructed, showing those kind of very simple building elements and the large expanses of opening windows to encourage cross ventilation. No glass, you'll notice. This is a cut through of one of the classroom blocks, again showing those simple elements. So laterite walls on the outside, the concrete ring beam which ties those walls together. We have thin reinforced concrete columns which are hidden in the laterite walls, and then earth for the ceiling, steel roof structure with a metal roof above. So onto the laterite. So laterite is a material that we haven't found much evidence being used in Niger, whilst it's kind of popularized in neighboring Burkina Faso and Mali, and it's being used quite a lot for schools. For some reason, it hasn't caught on in Niger. So we wanted to use this opportunity to show what could be done and hopefully kind of trigger a shift away from cement block schools and chunky reinforced columns to something built in laterite, which you can expose and kind of use as a facing material as well. So laterite is a kind of weird material to define. It's kind of often described as a soil or a rock. It is found all around the world in kind of the tropical zone around the equator. You can see in this world map, it's the kind of peach colored zone. So you find it across South America, Central America, much of Africa, also South Asia and the southeast of Asia as well. So right through that belt of the kind of equatorial regions of the planet. It happens where tropical climates create this kind of cycle of very hot weather and then very intense rainfall. They seem to be the kind of conditions where it forms. Now, it often has this kind of red-orange color due to its kind of high iron content. It's kind of got a lot of aluminium and iron content. I mean, this varies a lot region to region, so it always looks slightly different depending on where you dig it out of the ground. It's very porous, as you can kind of see from this image, so it fills with water underground, and then when you take it out of the ground and dry it out, it hardens as that water evaporates and is taken out of the material. It has been used for millennia in building. There's a particularly rich tradition in Cambodia and Vietnam, where it's been used in temples. This is from Angkor Wat from the 11th century, but also in much of South and West India, where it's found in all sorts of buildings. This is a church built in the kind of 16th century, I think, which is still there. But it's been used in Hindu temples for many hundreds of years in Kerala and Karnataka, amongst other regions. I haven't found so many examples of historic use in Africa, although it's certainly been used in Ethiopia. This is, again, hundreds of years old. Some of the temples at Lalibela are from laterite stone. If anyone happens to know of more like historic uses, I'd really be fascinated to hear. So do reach out in the chat. But there's been a kind of explosion of architects promoting the material, notably in Burkina Faso. I've already mentioned Francis Kéré, but other African architects and European architects who are working there have been using it too. So this is also spread in Mali as well. And so there are some beautiful examples of its use. And so we were sort of really being inspired by this and trying to kind of bring this movement to Niger, as it were. Now, I mean, it's sort of an obvious point to make, but there are huge advantages in terms of embodied carbon. Fired brick is a wonderful material in many ways, but it is extremely energy intensive in its production. You have to fire kilns to the best part of 1,000 degrees to fire bricks, which makes it a really problematic material in terms of carbon usage. Cement block obviously has Portland cement in it, which is, again, highly energy intensive in its production. And in the case of Niger, you often have to import it from Nigeria or Togo or Benin. Even compressed earth blocks, which in some locations, I've been a huge advocate for and love to use, but you generally need to use some cement content, even if they're hand produced. So that sort of increases the carbon, embodied carbon, whereas laterite, in the way we were using it, digging it by hand, just a few kilometers from the school, its embodied carbon is zero or negligible. As there's no kind of established use of it in Niger, we really spent a bit of time finding suitable laterite to use. So this is our kind of site team. So our Article 25 architect, Kodjo, is on the right. Our contractor, Sauter, is on the left. And then in the middle is Benjamin, who is very experienced in building with laterite in Burkina Faso. And he spent a few weeks kind of testing various spots around the outskirts of the city for laterite that was suitable for building. A lot of it's quite friable and not really strong enough to use in a building. But he eventually found this site, and as soon as he kind of got out of the car, he was pretty confident and said, this will be the spot. And apparently it was just the nature of the foliage that was growing on the site. He recognized as somewhere that good laterite would come from, and also the way that the rain was running off the surface. And so as soon as he saw both of those things, he was certain that would be a good site to use, and it proved to be correct. So the entire school construction is built using laterite from this very spot. All of it was cut out by hand. So these guys kind of cutting out by pickaxe, they cut out the rough blocks, and then they stack them in the sun for at least a month for it to kind of start drying out and harden. And then they were sort of driven by this tractor to the school. It was under 10 kilometers, I think, where the masons on site would kind of shape the blocks. They would sort of neaten them up using these hand tools ready for use, and then put them onto the building. you know, as soon as we saw these blocks, we were, you know, as an architect, you're thrilled. You know, they're just beautiful. You kind of get this incredible texture and mix of colours on the blocks. So I'm just going to flick through a few. I don't know how many of you are kind of design or architect kind of based, but I'm going to flick through a few pictures of the construction itself, just to show you kind of how it went. So because we built with laterite in Burkina Faso, but we hadn't kind of used this exact block. So we used the guards house as a kind of test bed, trying all of the masonry and testing if it worked first before going on to the classrooms, and it went pretty smoothly. So this is the guards house kind of going up, and then onto the classrooms. So it was really very fast to build with. Here you can see this is the rebar up the center of the columns. So the columns are constructed by building squares with the laterite with a hole through the middle, which you pour the concrete into. So this means that you don't need any shuttering, which is really useful because shuttering is expensive. In Niger, there's not much timber or board available. So to take that material out is really good. And it also reduces the size of the columns. These are very small. They're kind of, I think, 1,600 square columns inside. And here we're up to the roof. So the vaults are going on. The vaults, initially we wanted to use laterite for the vaults as well, but they proved quite difficult to do with the blocks. Like as soon as you got the blocks small enough, they weren't really stable enough. So we opted to make our own earth bricks with a small amount of cement to do the vaults. So these were all made on site. Like I say, with a kind of 4 or 5% cement addition, just to kind of make them strong enough. Again, we were using lateritic soil, so some of this soil came from the same site, just from the topsoil, so that the colour would match. And here you can see the kind of the vaults once they were completed. Like, really nice. And yeah, the classroom blocks were finished in early 2022, and I think the first block was finished a year or so before that. So they've been in use now for 3 or 4 years, and broadly been a great success. Yeah, here are the kind of students outside, and a complete block there. You can kind of see it was very similar to those initial visualizations. So here's some more shots of the finished classrooms in use. This is the shaded part where kind of kids they use it after hours as a kind of homework spot. Many don't have much kind of cool shaded spot back at home to use for study. So I think if we design this again, we'd expand these areas, if anything. But we use laterite in the buildings as well. So because the steel is by far and away the most expensive part of the buildings, in those buildings where you don't have such density of use, so the classrooms are full of kind of 40, 45 students. In the guards post and the latrines, you don't have that many students, so the kind of heat generated by the use is much lower. So we decided to get away without the steel roof and save a lot of money. So the guards post, this is the office building. These didn't have the double roof system, they just had larger vaults. You can see out of laterite. So here we're building the walls and the roof from laterite, which is very satisfying. The latrines as well. And even the water tower, this had a reinforced concrete frame, but was wrapped in laterite block. So despite being quite a small charity, we've tried to use this project to kind of learn more about the material, really, as we've used it. There's not a great deal of study into its use, particularly in an African context. There's far more in India, where it's been used on a more commercial scale. But we did the studies we could to try and figure out just how suitable this material was. So it's not, at least the laterite we have it doesn't have great compressive strength. So for a single story building, if it's kind of well designed, it's appropriate, but you wouldn't want to use it load bearing or over kind of multiple stories. So it's more a kind of enclosure. But we did do some tests and tested the blocks once they'd been mined over time. So we did see some improvement in the compressive strength over kind of 3 months, 6 months, a year. And we, anecdotally, this is the case. If you leave it for years, it becomes much, much stronger as it dries out and hardens. But it would be really, really interesting to expand this study and do it more formally. Really understand how much stronger that material could be, because that would open up more possibilities potentially. And in terms of the passive design, we got some measuring equipment from a university here in the UK to test the temperature through the day in the classroom and outside. And we found that in hot spells, we were kind of really improving the internal temperature with this double roof system. So as much as 7 or 8 degrees cooler than the external temperature, which is a vast improvement. It's really, really effective. That kind of is slightly kind of, this is the best case scenario. So through the morning, you would kind of see an improvement of 2 or 3 degrees, and then by the afternoon, evening, it was often 4 or 5, and like I say, up to kind of maximum of 7 or 8 degrees cooler than the outside temperature, which is really considerable. So that was really exciting to kind of get some data to kind of back up how it feels. When you're in these classrooms, you feel it. It is much, much cooler. So that was quite exciting. We'd also set up some vocational training with some young women, many of whom had kind of just finished sixth form at the college. Niger is not a place where women are generally involved in construction work, so we really had to kind of challenge expectations. But the contractor got on board and then ran these kind of training courses using the construction itself as a test bed, and it proved really popular. It's something we wanted to build on, but again, COVID got in the way. We'd sort of established this connection with a vocational training centre that works exclusively with young women in Niger, and they were going to kind of take this on and run more training through the latter phases. But with COVID, this kind of couldn't happen, unfortunately. But it's something we'd love to try with the right project in the region in future. So I'm sure I've been talking enough, so I'll try and just wrap up quite quickly with a few reflections and lessons learned from the project before a quick Q&A, I think, with Mona. So laterite, I would say, proved a real success broadly. We think it is a very good alternative to cement blocks, which would be the kind of default material to use for schools in Niger at the moment. It's kind of competitive in terms of cost, arguably even cheaper. We think it looks fantastic, although of course that's really subjective. It performs well in terms of robustness. Both this school and the one we built in Burkina Faso are standing up really well a few years in. So on that front, we think it's great. The big challenge with laterite that we've encountered is in terms of winning over the hearts and minds of people in Niger. Not everyone loved it at all. I think there are aspirations amongst many people for, a leap into modernity, and modernity means copying Western building practices. So there's a big kind of favoritism towards glass, towards composite panels, towards steel, towards concrete. And that's something that we have to deal with on all of our projects to some degree, and kind of convince people the benefits of materials that may lie closer to hand, I would say. But yeah, I'm sure many of you will have encountered this in one way or another. In terms of the roof and the passive design, it worked really, really well. But the steel roof that we designed is quite expensive, particularly after the kind of hike in price during COVID. We found it's not really competitive with the kind of school building programs or the low cost kind of that we would be looking for if we wanted to roll out the design. So I think that is something we could definitely address. There are ways of getting those benefits without using that much steel. And so that would be a case of refining the design and coming up with something slightly less extravagant. It might not have the kind of architectural flourish of this kind of big flying roof, but I think that you get most of the benefits of cooling just by creating an air gap, and that air gap could be much smaller, I think, and would still bring most of the reduction in internal temperatures. That's the impression I get, having kind of spent time in a lot of different buildings in and around Niamey. So I think that with some real kind of investigation in that roof design, we could refine it and make it much more effective. In terms, hi, Mona.
Yes, sorry, I'm just conscious of the time, and the chat is buzzing with quite a lot of questions. So if you don't mind, if I just redirect the last couple of minutes, and particularly a couple of the questions that are coming through are about the connections and the binding material. So what's the binding material you use for the wall itself? And then in terms of the connections between the walls, what joints are we looking at?
So in terms of the binding material, we actually have a cement mortar here, which I was a bit wary of, just because you're using a natural kind of earth-based material, but so far so good, and the engineers were kind of happy with it in principle. If there was a kind of tradition or availability of lime around, I would sort of really want to investigate that, but so far it seemed to do a pretty good job. In terms of the connections, I'm not quite sure what's the specific question on that. We've got
it's actually about the cement mortar joints. So I think you've covered that.
Yeah. Okay.
Yeah. And then sorry, I'm just looking through the questions really quickly. One of the suggestions actually was maybe instead of the steel on top, one can put solar panels, which could help with the costs of the school. But that's perhaps one thing to consider.
I think that's a really interesting idea. Yeah.
I think actually that covers all. I actually also just had a question. You mentioned that when you showed your cross section, that the laterite floor was raised a little bit higher, and you can see that in the picture, right? The flooring is sort of 3 steps higher, because you said it doesn't do well with water. What exactly does that mean, in the sense that, you know, these are buildings that do the protection work from water anyways, but is it in terms of like flooding or?
Yeah, it's flooding specifically at this site. So there was a risk of flash floods. So there's been flooding on that site previously. So we had to kind of raise the building up. So yeah, we were worried about those moments when there might be water kind of sitting against the laterite, and we weren't confident how the laterite would age over time if that was happening, you know, repeatedly in the rainy season. We've also got the kind of the wide brim of the roof to keep as much rainwater off it as possible. It seems that, you know, some of the buildings don't have that, and they're doing absolutely fine. They seem to be kind of wearing really, really well. But we just don't have much data on this, because it's not a material that's been used a great deal. So we're sort of, you know, you have to try and balance risk with robustness.
Which is actually bringing me to the second question, because some of the photos that you showed in terms of the buildings, for example, the church in India, the Angkor Wat, and the churches in Ethiopia, those are multi-story buildings. But you mentioned that it takes longer to reach that type of strength, and so I think there was just a bit of disconnect between. I sensed the recommendation to go for only single-story buildings, but I saw the pictures of these much bigger structures. So curious if you know if they use different reinforcements, or if it is just that it comes with time and it's really just a question of data that's lacking at this stage.
Yeah, I mean, to be honest, I'm speculating quite a lot. I suppose the recommendation I'm giving is based on the laterite we had in Niger, which is quite weak, at least when it's taken out of the ground. My view on Angkor Wat and those churches in India would be that perhaps they have stronger material, for one, perhaps. And we know this from our study, but also anecdotally from around the world, it does improve strength over time, and the weathering, both from the open air and the repeated rains, seems to make it a much harder material. But also maybe on those churches, there might be a stronger stone structure behind it. I'm not entirely sure. So yeah, sorry, it's a lot of different factors probably at play with that.
And it is quite expected when we're starting to look at these materials from a different perspective and to look for different types of documentations for the properties of these materials. I think it's quite a worthy exercise overall. And I see maybe the last question, because we're running out of time. We've run over time, but I'm still seeing more questions come through, particularly on the embodied energy in laterite of the number that you brought, which was negligible in millijoules per kilogram. Is there a citation for that? Because Jigedale is asking, because they do work in India and they would like to be able to cite that work.
Yeah, I'm afraid there isn't. This is very rudimentary kind of calculation based on the fact that it's basically what the guys ate for lunch. That's the energy going into it, right? They're digging it out and more or less carrying it to site. I suppose if we're being stricter, there's the petrol of the tractor to get it from there, but it's it's negligible in the grand scheme of things. There's no energy produced apart from the human energy of digging it out of the ground. That's very, very different from firing kilns to 1,000 degrees with, for days on end to burn your bricks. So yeah, I'm afraid no citation, but yeah.
Yeah, so no citations yet, but we'll wait to see the next publications on this. And then again, another question: what's your extension to the hygrothermal aging of these blocks? Maybe hydrothermal. I'm not sure what hygrothermal is.
Yeah, I'm afraid I'm not clear on the meaning of that either.
Yeah. This is from Sameh Balti. I don't know if you wanna unmute yourself. If you can unmute yourself and make a comment. I'm not quite sure.
I think with many of these things, you're probably sensing there is a lack of research into this material. It hasn't been, as far as I'm aware, it hasn't been explored a great deal, particularly in Africa. And so if anyone's willing to kind of fund some research or put us in touch with people, we have all of the expertise on the ground. Like we know the builders, we know the masons, we know people who build this all the time. And the proof is in the pudding in terms of its success. But yeah, if we really want to make this more appealing to governments, to widespread school building programs in the Sahel, which I think is perfectly appropriate for, then we do need to back it up with better data. And so I think that should be the next step, really getting some more in-depth research underway with the backing of institutions or bodies such as yourself. It'd be a great study to do. I think there's so much potential for this material, and yeah, hopefully we can. We've recently won some awards from this, and I'm hoping it's going to get some wider coverage. And with our advocacy, who knows? We really think that this is being underutilized, and we can stem the tide of building with cement, which is what's happening, and it's better in so many ways than that. So, yeah.
Yeah. So on that note, actually, I am putting in the chat the link of the submissions for the compendium on bio-based materials. We are looking for examples like this. We've seen quite a lot of interaction from the audience for today's webinar who work with this material and with other similar materials and other bio-based materials. So please feel free to put in the submission. We recognize that data at this stage is quite a challenge, so there might be some questions you're not able to answer, and that's fine. But please do put in as much information as possible. We are trying to start to build that knowledge base and make sure that it's accessible to everybody. So we look forward to seeing submissions from you, and I've put that link in a chat. On that same note, we have a few other, we will be sharing the presentations, but also I have mentioned the 10 recommendations, the 10 whole life cycle recommendations, and I'm putting a link on the recommendations to the chat, as well as a link to submit the resources or submit experiences. You talked about the rehabilitation of this building, which is one of the recommendations of these 10 recommendations in terms of reusing whatever possible before starting anew. So that's also another space to showcase this work. And this invitation is, of course, also to the audience with all the work that they've been doing. And then finally, to join the Materials Hub, where we hope to bring together different people who've been doing this type of work. I'm putting also the link in the chat, and then we will be sharing the slides with everybody who's joined today, and we look forward to having more presentations of this sort as we move forward. So please stay tuned, and we look forward to seeing you all again in other presentations. Thank you so much for your time. And thank you, Toby, for this example. It's really nice to see the work that's being done everywhere, and lovely to see the interactions in the chat and the energy that the audience has brought. So thank you, everybody, for your time. Apologies for running over time, but we appreciate that you've stayed with us the 10 extra minutes as well. It was definitely quite an interesting time that we spent together. Thank you. So with this, I'm going to close the webinar, but thank you so much, everybody, for your time, and I look forward to seeing you again.
Thanks, everybody. Thanks, Mona.